everyone, this is Arnoud, whizbiz.com, and today let's talk a little bit about so-called resistor and capacitor decade boxes. When I was experimenting again with frequencies of a monostable multivibrator the other day, I was in need of a simple way to measure the influence of different resistance values on the output. Sometimes you just want to have an easy way to gain insight into the frequency behavior of a timer, a monoflop, or another oscillating circuit. Of course, it is possible to do what I have done until now, and that is to provide a small potentiometer with wires and use that in your circuit. After experimentally determining the desired resistor value with it, the value of the disconnected potentiometer can then be measured with your regular multimeter. But of course this requires disconnecting and then reconnecting the potentiometer each time, and up to the point of actually measuring it, you might not have a clue about the actual value it has. This is exactly the reason why I already devised some kind of modular pluggable potentiometers for my own designed experiment board. In this way, different potentiometer values can easily be swapped. Just switch it for the desired value. The measuring afterwards can easily be done via the already connected wires of these DuPont pins on the board. This already gives, of course, a bit more flexibility in respect to the resistance values that you try to figure out, because a potentiometer can be chosen that is already in the intended range of the experiment you're doing. For instance, determining a useful fixed resistor value for such a kind of project. But as with the loose potentiometers with wires, the experimentally found value will have to be measured afterwards with, for example, your multimeter. This might be in itself a useful solution for resistance values, but if we want to experimentally determine the value of an inductor or capacitor in this way, it becomes a little bit more difficult. Simply because the adjustable range of the variable version of these components is usually relatively small. For example, an adjustable capacitor such as this one can be tuned only by a few of tenths of picofarads. For coils, a tunable core can be used, of course, but even there the effective range of the component is often too small for effective experimentation with the circuit on the test board. To solve this, so-called resistor and capacitor decade boxes have been invented. These contain a series of resistors, capacitors or coils that can be stepped to obtain a resistor, capacitor or coil with a specific value. It is possible to build a decade yourself, of course, but most people will simply buy one. The reason I didn't have one myself is because when I looked, they seemed quite expensive for the few times I could really need them. So up till now, a workaround with a potentiometer was fine for me. However, in my search on the site of our Chinese friends, I came across several advertisements for very affordable decade boxes. Most of the time the settings were not made with a whole series of switches as in the more expensive models, but with simple PCB jumpers. However, there was also a version of a very affordable decade box with dip switches. That really seemed like a nice intermediate solution. It might not be as robust and heavy duty as having real switches, but it's a lot less fiddling than with these loose PCB jumpers. And since I certainly don't use a decade every day, this all seemed very useful and affordable. So I ordered the resistor and capacitor decade boxes I found, and here they are. So this is the resistor decade, which can basically be thought of as an adjustable resistor from 0 to 10 mega ohm. Well, just up to 10 mega ohm, that is. Basically between 0 and 9.9999999. Is that already 8 nines? Yeah, I guess. And that all in steps of 1/10 of an ohm increments. With these dip switches, the tenths are adjustable. With this dip switch, the units, steps of 1 per switch. In this case, all the resistors are already in series and you tap it at the setting you make. So the idea is to activate only one switch each time. The last one, it says 10, but it should read 0, I guess. It's just a bypass of the resistor series at this stage. So if all the switches are set to 10, the resistance would just be 0. And if all the switches are at 9, the maximum resistance of almost 10 mega ohms can be measured between the 2 points of this huge terminal block. Such a decade box simply contains a whole series of individual components that can be switched in series, or in the case of the capacitors, in parallel, at will. Each decade is formed by 9 of the same component. It doesn't add up to 10, but only to 9, because you also have 0 as one of the settings, which is of course simply a bypass of that stage. The lowest can then be used to make 1 through 9, and when set to 0, the 10 can be made with the next decade series. Each in this way configurable sequence of units, tenths, hundreds or thousands differs in a way from the previous one by a factor of 10. So with, say, 3 decades, values from 0 to 999 can be made. Okay, so here we have the tens, the hundreds, the thousands, the 10,000s, the 100,000s, and the 1,000,000s. So that's the megas. 8 stages in total that can be set from 0 to 9, and the final resistor is a series connection of these settings. The SMD resistors seem to be 1/4 watts. That would mean this should be SMD housing 3216, I guess. Not completely sure. But from my point of view, the wattage is not that relevant, because usually such a resistor decade will be used to play around with the frequency determining circuits of an oscillator, for instance. If you really want to experiment with power, it's better to test experimentally with a few loose power resistors, and you don't actually need that configurable step precision anyway. Alright, so here we have the other one. This is the capacitor decade. Again, dip switches for the settings. With this one there are only 7 decades. This makes it an adjustable capacitor that's adjustable from 0 to 10 microfarads in steps of 1 picofarad. So here the same as with the resistor decade, and now rows of 1 picofarad, 10 picofarads, 100 picofarads, 1 nanofarad, 10 and 100 nanofarads, and finally a step with 1 microfarad capacitors. This seems to be the SMD 1608 form factor. And note that with this capacitance decade box there are 10 similar components connected in parallel, and with each dip switch a similar capacitor is added at that particular stage. With the resistor decade box, on the other hand, the components are connected in series, and with one dip switch you choose where to tap the series connection of 9 components. So this one has only 9 components, because one switch is used to bypass the whole decade stage. That makes sense, of course. The resistors you put in series for the value to increase, whereas capacitors, the value increases as you put more of them parallel. There are 4 mounting holes here. This here could be the manufacturing date, by the way, I guess. If it is a fairly new product. Probably it was produced a little over 3 months ago then. This might be the reason I only recently came across these PCBs online. I do have to say that I don't like this huge terminal block. It's quite large. I think I will desolder that one with hot air, and that will also make the whole thing a little less tall, because it does stick out quite a bit. I think it would also be nice if I had some female DuPont headers on here, so I can connect experiment wires like these directly. That will make it more useful if the circuit is built on a breadboard like this. And also I think it would be very handy to be able to connect these small banana plugs, these 2mm plugs, so that I can make a wire to my multimeter to measure the final set values. Alrighty, these things look very convenient on the first inspection, but I most certainly would like to change the connection options a bit and have a small casing around it. That would make it more useful for me on the workbench and for my specific use. So I think it would be useful to desolder this one and design a small enclosure or casing for it. Alrighty, so fast forward, it's all done. Designed in Blender and printed in red PLA with the holes for the DuPont and the 2mm banana plugs in the top here. Hope it fits. Yeah, I guess so. By the way, should you like to print these things yourself, I'll make the STL files available. Just follow the link in the description and you'll find them. Fits nicely and snugly in here. I didn't bother with screws to mount it all. Just printed some pins that stick through the holes and made a small lid up here in the top section to cover up the connection to the PCB, and from these connectors here at the top. Alright, in this way everything is very slim and not that high as with this screw terminal. Okay, fast forward again, and there we are. All the connectors in. 2 DuPont connectors in the center, and at the sides the 2mm banana plugs that I would like to have for my measuring instruments. I think you just have to pull the DuPont in an in-circuit situation to measure the final setting of these decades. Small lid goes up here. Hope it fits. Again, I'll make the STL files available for you, and perhaps this might be a nice time to subscribe to my channel, or at least give me a thumbs up if you like what I'm doing in these videos. And there was a flash forward again. Like to show you my finished products with the connectors on, and perhaps this is a nice time to conclude this video with a small try. I could connect the DuPont connectors, of course, here. But perhaps I would like to use the 2mm plugs now. Let's first try the resistor decade with 8 stages. And I have already put all the dip switches number 10 in the switched on position. So everything is bypassed and there should be no resistance at all. My multimeter is a little bit thinking, and yeah, it came to the conclusion there is no resistance at all. Let's give it a try. For instance, here with the 100 ohm stage. Let's first bypass it. Okay, we've got 0 on our multimeter, and let's give it a try in the 100 ohm section of this decade. For instance, number 8 should give 800 ohms, I guess. Let me have another scale here, and yeah, fairly good, about 100 ohms. And so it's bypassed. Let's go to the 1K resistors. For instance, number 6 Nothing going on. Oh, I have to rearrange my scope, of course. Yeah, there it is, 6K. Well, nearly 6K. That's okay by me. Fair enough. Bypass that stage and go to the 10K decade stage of this box. For instance, number 4, that'll be out of range, of course. About 40K then. Fair enough, again. Very handy. You have to remember to bypass it if you don't use that stage. So, bypass it. And we go all to 0. And let's try the mega ohms here down. That should be 3 mega ohms. Or somewhere near 3 mega ohms. Yeah, it is. Let me try 1 mega ohm. Fair enough again. Very useful. Useful stuff. Yeah, okay. So another try with the capacitor decay then. I'll use another test instrument for that. First, let's connect it. Let's use the DuPont connectors here. This one only has 7 stages, and when everything is off, it already has 40 picofarads of capacity. Perhaps that's the test leads. Well, it makes me wonder if these first 2 stages with 1 picofarad and 10 picofarads capacitors in them are really useful on this decade bridge. I doubt it. Let's head for the 1 nanofarads capacitors here. If I choose only number 5, of course, yeah, that will be not 5 nanofarads, but only 1 nanofarad, because all these capacitors in this row are put in parallel. So you need to think a little bit different than with the resistor decade. This is 5 capacitors of 1 nanofarad. Nicely gives you 5 nanofarad value. This is the 10 nanofarad stage. Let's put in 2 and take a look if that is really around 20 nanofarad. It is. Very nice. Of course, there is also a row with 100 nanofarad capacitors. Let's switch around 4 and see if that adds up to 400 nanofarads. There it is. Yeah, fair enough. Very good. Around 400. So it needs a little bit thinking about what you're doing. All the capacitors here are put in parallel, just so it just adds up. So this will be 2 microfarad then. The last stage it is. Yeah, fair enough. Capacitors are only 10% precise, but well, you can make all the values you'd like up to 11 microfarad. That is. Let's put everything on and give it a final test how high it can go. So we have everything switched on here. Takes some time. Yeah. All right. Let's give this a try. All the capacitors parallel. All the capacitors of the whole thing is, yeah, it is about 11, just up to 11 microfarads. Wow. Again, very useful stuff. And perhaps give the resistor decade also a try with this measuring instrument. We switch on, for instance, 5K here. Let's see if that's... it is 5K, but a lot more. 1 mega ohm. Oh, I see what the problem is. I forgot one switch in the mega ohm section. Let's do it again. What's going on? Yeah, as I already told you, this needs some learning for me. I guess we're there. Yeah, I forgot to bypass the 1 mega ohm stage. So, very useful stuff, I guess, every once in a while when you need it on your electronics workbench. Perhaps these things will come by in future videos of mine. For now, I'll be playing around a little bit with them and hope to see you with my next video. Until then, happy hacking!